Welcome back. We just completed the proof of the alternating series test and its corollary. Those two happens to be the most difficult and time-consuming proofs. The others are a little bit easier. And for that reason, there must be some student who just skipped that video and coming directly to this one, or even if they went through, didn't really understand too much. For those students, let's review preliminaries a little bit, and let's talk about the main tool that we are going to be using, which is Cauchy sequence theorem. A sequence converges if and only if the difference between the arbitrary terms am and an go to 0. The right-hand side is often called Cauchy condition or Cauchy criterion. And this am minus an is actually a double sequence. We have two indices m and n that are unrelated, except that they are both becoming infinity. For example, if m and n are related such that m is the next number of n, like m is n plus 1, or m is n squared, kind of related in alternative fashion, or anything, any algebraic or any other kind of relation, no, they're all out. M and n must be independent and unrelated. In other words, this expression which I just highlighted can be really complicated. So what's the point considering something that complicated? Well, there's a trade-off as a matter of fact. The left-hand side, the convergence condition is good. We have just one index k. However, in order to use it, we have to have a candidate of the limit. For some reason, if we cannot guess it, or the technicalities of the proof forbids us to do any kind of guessing, then we can't use this condition that we just highlighted. One way to handle that difficulty is to use Cauchy criterion. Now, an alternative form of a Cauchy criterion is right over here for series. What is a series? It's basically a sequence of partial sums. So if we put partial sums here, then instead of am minus sn, we're going to get am minus an, we're going to get sn minus sm. Because the convergence of a series is equivalent to the convergence of partial sums. So just apply Cauchy criterion to partial sums, and this is what we get. And what is Sm minus Sn or Sn minus Sm? Well, it's right over here. M plus first term, M plus second term, M plus third term, all the way up to nth term, if n is greater. And in the other case, we can simply switch m and n. Now, the full proof of Cauchy criterion is rather difficult, and you'll have to look up some other textbook. And the easiest one I found is the one by Spivak, Calculus by Michael Spivak, and here's the ISBN number for interested students. Here, let's go over to just one side of the proof. If the sequence converges, then Cauchy condition. The other direction is too difficult. Let's suppose the sequence converges. AK converges to A. Then this limit on the right hand side here can be rewritten like this. And all I have to do is to insert minus A plus A, which is equivalent to adding 0. So I didn't change anything. And then let's just apply the limit rule. Am minus A, that goes to 0 because we just assumed the sequence converges to A. How about A minus An? That also goes to 0 because we just assumed the sequence goes to 0. So what do you have? We get 0 plus 0, which is 0. And that's precisely what we wanted to prove in the end. There's a little bit of technicality regarding the absolute value, but I'm going to leave that to the students. After all, 0 is the only number whose absolute value is 0. And the other direction is too complicated, and we're not going to do that here in this class. Now, we just went through Coucy criterion, so let's talk about how to apply it. Excuse me, wrong cell. And let's apply that to absolute convergence. A series given by the absolute values converge, then the original series converges as well. And we use Coucy criterion. And let's say Sn is the sequence of partial sums of the original series. And what we want to prove is this Sn minus Sm goes to 0. But then again, we have another series given by absolute values. So let's say An is the sequence of partial sums for the series of absolute values. Then we are going to have something like this. Absolute value of Sn minus Sm is equal to, well, n plus first term plus n plus second term plus n plus third term all the way up to nth term. And then let's make this observation, this inequality, which is often called a triangle inequality. If all these AKs are all positive, then we'll have equality. If they're all negative, then we'll have equality too. However, if there are some positives or negatives, in the left-hand side there are going to be some cancellation. In the right-hand side, there will be no cancellation because everything is positive now after taking the absolute value. So the right-hand side, which I just highlighted, is greater. At least greater than or equal. And what's the right-hand side? That's actually the difference of two arbitrary terms for the absolute values, an minus am, partial sums given by the series of absolute values. And that goes to 0 because we just assumed that the series of absolute value converges. So what do we get? This sequence, absolute value of Sn minus Sm, is less than that sequence, which is going to 0, so we have to have convergence to 0 as well. And that proves the convergence of the original sequence. However, the converse doesn't apply. For example, here's an example of a convergent sequence which is not absolutely convergent. Please note that this is an alternating series. We have plus minus, plus minus, plus minus, and so on. And if you look at the absolute values, we have 1, 1/2, 1/3, 1/4 that decrease steadily down to 0. So this alternating series converges. If I remember correctly, that converges to natural log of 2. However, if you apply absolute values, then we'll have a harmonic series, and that diverges. Harmonic series just diverges to infinity. Why did I de-emphasize them in gray? This one maybe, but this one? Okay, let me just get this one back too. As a matter of fact, we'll learn that this is actually equal to natural log of 2 in the next section in power series. Now, absolute convergence and conditional convergence. If the sequence of absolute values converges, then the original sequence also converges. In that case, we say a series is absolutely convergent. If the series converges, but not absolutely like this one, then we say the series is conditionally convergent. And here's an example of conditional convergence. Now, the rearrangement, okay, we're not going to prove this one. This is a bit too difficult. If you have an absolutely convergent series, then if you rearrange it, it'll converge to the same value no matter what. But if you have a conditional convergence, then by rearranging, we can make that series converges to any real number or make it diverge even. So conditional convergence is much weaker than absolute convergence as far as the rearrangement is concerned. Okay, do we have time to go over the ratio test? Okay, looks like we do. So let's talk about it. Ratio test. The ratio has limit L, which is less than 1 than absolute convergence, and the greater than 1 divergence, and then equal to 1 inconclusive, which means Don't stop here, find another method. Okay, how do we prove that? Well, let's suppose L is less than 1, which means we can find out a certain R that is between L and 1. Because L is strictly less than 1, we can do that. If L is less than or equal to 1, we can't. When L is equal to 1, we cannot find anything in between. However, when L is strictly less than 1, we can do that. And then R is a little bit greater than L, so for sufficiently large n, this ratio an plus 1 over an, or absolute value of it, will be less than R, which is a little bit greater than L, but still less than 1. So that's how this convergence is working. Now, let's take n very, very large and then consider some estimation. Move this an to the other side, and then an plus 1 is less than R times an. And then an plus 2, consequently, by the same logic, is less than R times an plus 1. And do the same thing again, then we have R squared times an. Let's do it once more. There used to be an plus 3 over an plus 2, and flip over this denominator, an plus 2, to the other side. Consequently, we have, well, this inequality. Now this an plus 2 is less than R times an plus 1, so we have that. And apply that again, and we have R cubed times an, and so on. So just do it again, do it again, do it again, and what do we have? We have a geometric series, R to the k power times an. So what do we have? If we just add up the tails part of the series, then ak, the summation of ak, is actually less than this an, which came from here, times the geometric series, and geometric series convergence. So the tail part of the series converges, and that's enough, because head part from k is running from 1 to n minus 1, well, that's going to be finite anyway. So by the limit rule, we have to have a convergence. If L is greater than 1, then we'll have nth term test for divergence, because you see an plus 1 over an is greater than 1, so an plus 1 is greater than an. In this case, we cannot have convergence. an will not converge down to 0. So by the nth term test of divergence, we'll have divergence in the second case. Now, do we have enough time for root test? I may be rushing a little bit, but let's do it. Here's the root test. We can do the same thing, pretty much the same thing. This L is strictly less than 1, so we can find out a certain R between L and 1. In other words, n is sufficiently large, then this root will be less than R, which is a little bit greater than L. It can exceed L, but not too much. But less than R, consequently, far less than 1. Now, if we take nth power of each, then we have an in absolute value is less than R to the nth power. Consequently, we have geometric series again. And then let's measure the tail part of the series, and that's going to be less than the geometric series R to the nth power, and that's always convergent. Geometric series converges. So we have the convergence when L is less than 1. Now when L is greater than 1, in that case an is going to be greater than 1 for infinitely many n values. So the nth term test for divergence applies here. an in absolute value does not go down to 0, so we have to have a divergence. And that proves the root test.